Here the question is to evaluate the surface integral of this form over the same data as that in the last video lecture. F bar equal to y square z square x square, and the domain S, here the domain S is y equal to 0 bounded by x plus z equal to 1, x is equal to 0, z is equal to 0 and y is equal to 1. So actually you are supposed to evaluate the confined region in the plane y equal to 0. But here the question is to evaluate this using Stoke's theorem. So this is the important part. Here we are supposed to evaluate the surface integral using Stoke's theorem. So let us take the Stoke's theorem first. It is double integral del cross f bar, the curl of the vector function dot n cap dA over the surface S is equal to the line integral along the closed path C f bar dot derivative r bar, where this surface S is a continuous, smooth, orientable surface which is bounded by this closed curve C, which consists of three piecewise continuous smooth curves. And the figure already I have explained in the last video lecture. So let us start working, and the question is using Stoke's theorem. So in order to evaluate this surface integral, we'll evaluate the line integral along the closed path C. Let us see the first path C1. This is the C1 path, and when we are evaluating the line integral, always traverse in the anti-clockwise direction. So path C1, it is from this point till this point. But this part, path C1, is a part of x-axis. So the equations to the path C1 are y equal to 0 and z is equal to 0. Where x is bounded between, see, this is the point x, this is the point on x-axis, and that is 1, 0, 0, and this is origin. So x is bounded between, and mathematically we write this statement x bounded between 1 to 0 as this. Therefore dy is equal to 0, dz is also equal to 0. And now let us evaluate the line integral along the open path C1 f bar dot derivative of r bar. That is equal to path C1. This is the dot product of two vector functions, and this is f bar given here, where the components of derivative of r bar are dx, dy and dz. So the dot product of these two vectors is a vector function, that is y square dx plus z square dy plus x square dz. This is along the path C1. Let's use this data of the path C1. Y is equal to 0, so this term tends to 0. Second term, dy is 0, and therefore this second term also tends to 0. And in the third term, dz is 0, and therefore this is also 0. So the value to this line integral is equal to 0. Let us see the value to the line integral along the next path, that is path C2. Along the path C2. Path C2 is the portion of z-axis, and it is bounded between, you can see this path C2 is from 0, 0, 0 to 0, 0, 1. So the equations of the path C2 are y equal to 0 and z equal to 0, where x is bounded between 0 to, x equal to 0, y equal to, equations of the path C2 are y equal to 0 and x is equal to 0, where z is bounded between 0 to 1. You can see the z is 0 here and z is equal to 1 there. So z is bounded between 0 to 1. Therefore dy is also equal to 0 and dx is equal to 0. Let's evaluate the line integral along the path C2, that is f bar dot derivative of r bar. Again, along the path C2, the line integral, this dot product is a vector function y square dx plus z square dy plus x square dz. Y is given to be 0, so this term tends to 0, dy is also 0, this also tends to 0, where x is 0, so this also terms tends to 0, and the value to this line integral along this path C2 is equal to 0. Now let us try to identify the path C3. Path C3 now. Path C3 is again a straight line, but it's not a section of x-axis, y-axis or z-axis. It's a distinct line in xz plane. So whenever you find a distinct line or a curve in any of the surfaces, in any of the planes or in any of the surfaces, first question we always raise is where does that line or the curve lie. Now this line lies in the plane, that is y equal to 0, in xz plane, that is, and the equation of that line is x plus z equal to 1. Therefore I'll make the things ready first. Y equal to 0, I'll write this as z is equal to 1 minus x, or else you can write it as x equal to 1 minus z as well. Therefore dy is equal to 0 and dz is equal to minus dx. Now evaluating the line integral along this path C3, f bar dot derivative of r bar is equal to, it is scalar function again, y square dx plus z square dy plus x square dz, where y is 0, therefore this term tends to 0, dy 0, therefore this term also tends to 0, but this is a non-zero term. So let's see that part. It is x square as such, and dz substitution is minus dx, so that is minus dx. So we observe that this is a line integral along the path C3 and with respect to x. So now let's see the limits for x. This is your path C3, and since we are traversing in the anti-clockwise direction, it is from this point to this point. X is 0 here and x is equal to 1. So x is bounded between 0 to 1. And when we evaluate this, it is minus x cube by 3, where x is bounded between 0 to 1, and the value to the line integral along this path C3 is minus 1 by 3. And let's recall, in the last video we got the value to this surface integral to be equal to minus 1 by 3. We have evaluated right now in this lecture the value to this line integral along the closed path C, where this surface is bounded by this closed path C, and got the value along the closed path C, f bar dot derivative of r bar is equal to sum of all the three line integrals, and that is equal to minus 1 by 3. The question here is to evaluate this surface integral, and therefore the value to this surface integral is equal to, therefore del cross f bar, surface integral over the surface is del cross f bar dot n cap dA is equal to minus 1 by 3. So it is exactly the same what the value which we got it in the last video lecture.